Hello, welcome everyone. Today we have uh, Wren Usiatynski, and she will have a technical talk about her experience in industry and research. Uh, the title is Synopsis of Industry and Research Experience as an Early Career Professional in Coastal Engineering. So I have to mention this is a part of NHERI GSC workshop and mentoring program, and we are honored to have Wren as our speaker. Mentioning NHERI GSC, we are a community of grad students and professors, early career faculty members who work natural hazard research, from earthquake engineering to coastal engineering, wind engineering, whatever you can think about. And you can connect with mentors by joining us. You can connect with mentors. You can attend workshops, and we encourage all our members. And also, you can learn how to have an impact uh, on the natural hazard research and practice, and gain leadership skills and also funding opportunities that we have for you. By scanning this barcode, you can fill a form. It's easy and free, and you can join us and become a member as NSF, become a member of NSF NHERI GSC. So Wren is our today's speaker. She's a Department of Defense Smart Scholar. She's coastal engineering student at University of North Carolina, Wilmington. And also she had great experience in industry. She was working as a coastal engineering specialist in Anchor QEA. And also she worked in US Army Corps of Engineers projects. So she is going to share her experience on how she got her job and positions and scholarships. And also she's going to talk about her most interesting projects. We welcome Wren to give us her talk.
Alireza, and good morning to you all. So, as Alireza mentioned, I'm a senior at the University of North Carolina, Wilmington, or UNCW, and I study coastal engineering. I'm the founder of the Society of Women Engineers at UNCW, and then my experience is as an intern at Anchor QEA, as a student research assistant at the U.S. Army Engineer Research and Development Center, or ERDIC, and I worked under one of my professors on his research project. And then finally, I'm a science, mathematics, and research for transformation, or SMART scholar for the U.S. Army Corps of Engineers, Jacksonville District. So you can go on to the next. Yeah. So starting out, I'll share my experience in industry, beginning with Anchor QEA. Sometimes I might reference it as AQ or Anchor, but it's all the same thing. This is a national environmental engineering firm with QEA standing for Quantitative Environmental Analysis. I was first introduced to the company through my mom's pickleball friend, funny enough. You really just never know what connections are going to end up benefiting you. But essentially, she just mentioned how I was at the time a sophomore undergrad studying coastal engineering. He immediately recognized that discipline since two of his coworkers at the Syracuse, New York office, which is my hometown, are coastal engineers. From there, I expressed interest in the summer internship. And so we got in contact and I visited the office over my winter break. And then after that visit, I applied for their internship program, which involved just a standard resume and cover letter submission. This application was then followed by an interview during their intern stay. But unfortunately, since I was in North Carolina at the time, I wasn't able to attend in person, but instead participated via Zoom. Um, Over the summer, I had the chance to work on a bunch of cool projects, a few of which I'll take a deeper look at today. But once the summer was over, I took advantage of an internship and engineering course that's offered at UNCW. So that's just a way to get academic credit for internship experience. And I stayed on at AQ, which ultimately switched my official title to engineering specialist as opposed to coastal engineering intern. Um, just looking back, I'll always be so grateful for such an extraordinary opportunity in Syracuse, since Syracuse is not super close to any nearby coastlines. Um, but yeah, so the first project I'm gonna share takes place in Santa Cruz, California. This project had a marina that experienced a long wave event that completely ripped up a ton of the floating docks and resulted in extensive damage to boats that were being stored there. Anchor QEA was hired by the municipality to quantify the return period of the event and see if there was a solution within the municipality's capability and budget to prevent or armor against a similar event. AQ was able to run the event in Delft 3D. Delft 3D is an open source numerical modeling software that can be used to simulate hydrodynamics, sediment transport, waves, and more. In this case, it was used to model waves at a lower resolution for the greater northern half of Monterey Bay, with a goal of just getting some inputs for a smaller, higher resolution model of the harbor that you can see here. This was done using XBeach as opposed to Delft, since Delft 3D was unable to provide some of the graphical results that were needed for such a long period wave. XBeach is also an open source numerical modeling software, but can focus on more extreme events and was able to output the needed results, including this demonstration of water level over time. You can see that as this wave propagates through and reflects off the back of the marina, there could definitely be some significant disruption of any floating docks or boats. Um, this result, sorry, this result was then shared with the municipality, where the team at Anchor got the feedback that it doesn't get more accurate than that, which, as any modeler knows, is a huge pat on the back. So next up, I'll go over a project which involved little to no modeling, but required a bit of data collection and some verification calculations. This was part of a long-standing AQ remediation of the Housatonic River, which is about 150 miles long and runs from Massachusetts to Connecticut. The river was split into reaches in order to do the cleanup, and one of those reaches was Woods Pond, which is located in western Massachusetts. This region of the river required dredging, so just removal of some contaminated sediments, and sediment capping, which is done to isolate contaminated sediment from the surrounding environment and is generally done when dredging is not feasible. This required a process of elimination to determine if any existing conditions would interfere with this effort. Two of these forces included wind waves and icing. The wave calculations were done using ACES, or the Automated Coastal Engineering Systems, which is an Army Corps tool that is frequently used to determine the required armor stone sizes for a project. The ICE calculations were done by using the ICE Engineering Research Group Cold Regions Research and Engineering Laboratory, or CREL website, which gives a calculation method for ice thickness based on daily temperature. Both of these calculations were done just to ensure that the waves and ice wouldn't disrupt the armor stones placed for sediment capping. Another concern here was the flow rate. So they already had some calculated flow rates, which were just checked against the cap's maximum shear stress load to make sure that there wouldn't be any disturbance there. So now moving on to a hydraulic analysis. This project involved the partial demolition of an old building owned by National Grid that bordered the Hudson River, and that eventually became a safety hazard. And so just to resolve this, they decided to take the riverside wall of the building down to an elevation where it would not be overtopped, and it would not be overtopped by like strong flow rates. And they even left 5 feet of wiggle room. In order to determine this elevation reached by these flow rates, a 1D HECRES model was used using USGS flow data as input. One interesting method was provided by on-site observations and pictures taken during an extreme flow event in 2011. These were then scaled and could be used as a way to almost calibrate or validate the model's elevation outputs. You can see in the top image that the model elevation output was a bit below the planned demolition level. The lower image then just shows the HEC-RAS model and transects that they used, and you can see that there are three bent transects. This was due to a curved dam, which could sometimes get overtopped during these high flow events and wasn't correctly accounted for when using only transects that just go straight across the river. And so the final Anchor QEA project I'm going to touch on is the NUN library. So NUN stands for the Network for Engineering with Nature. This was a more research-based project, but it's what I spent the majority of my internship working on. So NUN is a collaboration between industry and USACE to further USACE's Engineering with Nature, or EWN, initiative. As part of Anchor QEA's role in this network, they're developing a user-friendly guidance library that contains various reference documents and tools that are both internationally and locally applicable. The focus here was to be just super user-friendly and allow searches by engineering professionals to filter by region, project type, tool style. This could be like a document or a map or a database. Accessibility, so think like link versus a required download. What data is included, if any, and then who owns or published the tool. So yeah, now I guess speaking of research a little bit, let's move into some insights into physical modeling. So I first visited the ERDIC Coastal and Hydraulics Lab, also known as CHL, in Vicksburg, Mississippi, back in October of 2024 for a professional development opportunity that was provided for 30 undergraduate and graduate students under funding from the U.S. Coastal Research Program, also known as USERP. To prepare for this week of missing classes, over the summer, I emailed each of my professors, one of which was Dr. Ryan Mirez, and he told me about his future research trip to ERDIC. He asked if I might want to join, and I, of course, said yes. Throughout this time between October and summer of 2025, I gradually prepared myself for the upcoming 2-month-long research trip. And so before I move on here, I'd just like to spend a moment to sincerely thank Ryan Mears for providing this opportunity and everyone involved at the collaborative universities, as well as all ERDIC CHL employees, including Duncan Bryant and Cassie Everett. So now moving on to an overview of the project. Starting with the proposal, which was sent to USERP and had funding from the U.S. Army Corps of Engineers. The proposal was titled Breaking Wave-Induced Rapid Beach Profile Evolution in the Inner Surf and Swash Zones. This was sent in by Ryan Mirez as lead PI, and then Blair Johnson, Tom Su, and Jack Paleo as co-PIs. This just was sent in to investigate mechanisms that drive inner surf zone and swash zone sediment transport and the resulting morphodynamics. This was done through mimicking conditions that will generate intensive sediment transport events in a wave flume. This proposal was sent in collaboration with the University of Texas at Austin and the University of Delaware. It was also sent in parallel with a proposal from the University of Florida and University of Illinois. Although I am a graduating senior and will not be involved in the final objectives of this project, they primarily include updating the physics in said interfoam to reflect research observations. And said interfoam briefly is an open source high resolution turbulence resolving two-phase model. And so the end goal is to help forecast which areas of a beach may experience little to no sand loss or substantial sand loss during coastal storms. Another objective here is to share findings through academic papers, journal articles, and conference presentations. So as mentioned, the facility was located at the ERDIC CHL. This lab had a 5-foot flume, a 10-foot flume, and wave basin. UNCW and the University of Delaware were primarily working in the 5-foot flume, which had a 1:30 slope using 0.15 millimeter well-sorted sand. The University of Texas at Austin was primarily in the 10-foot flume using PIV, which is particle image velocimetry. And so PIV can just track particles and the goal was to get a better understanding of the highly turbulent inner surf and swash zone. Lastly, the University of Florida and University of Illinois teams were working in the basin and also tracking beach morphology and sediment transport. So moving on to a more detailed look at the experiment, this table shows the types and quantity of sensors used at one time. So the figure here represents the approximate location of each sensor station in the flume. Shown in the table is the location of each sensor at each station. This included wave gauges to measure water surface elevation, ADVs, or acoustic Doppler velocimeter, as also often referred to as vectrinos, and vectors, which are another type of ADV, to measure point velocity. The reason for using both ADVs and vectors was just because of the quantity of what was available at the time. There were also ADPVs, and which are just a profiling velocimeter. And then these are also used for velocity profiling. The OBSs, which are optical backscatter point sensors, are used to measure suspended solids concentration. And then UDMs use sonar to collect bathymetry data. And this was focused in on the swash zone. The pore pressure sensors were placed within the bed and collected pressure data. Finally, the CCP pluses are a second iteration of the CCPs, which are conductivity concentration profilers. And these were developed under a previous grant by members of the teams from UNCW and the University of Delaware. Outside of the flume, we also had a Blickfeld Cube 2 LiDAR, which took data between runs and during each run at a relatively low resolution. There was also a Faro LiDAR owned by ERDIC that got high resolution data with imagery, and that was done between every few runs, I believe every 4 runs. Lastly, there were 2 cameras, one that was down facing on the flume and another one that got a cross shore view. So yeah, so to show this further, here's an example of one of these stations. Just quickly going through, the marker A has 2 OBSs, B has 2 side-facing ADVs, there's 2 CCPs at marker C, and 1 ADPV at the end there. You can see that the CCP probes are sticking into the sand, and that's where they're going to collect data on sediment concentration and aiming for the fluidized layer of the bed. So what's going to ultimately get a bit more fluidized there. Okay, so during the 8 weeks that we were there, we took 56 runs. These were split into 3 wave cases, a solitary for a single swash event, as you can see here, and then there was also a double solitary wave, and then some regular waves. So interestingly enough, the double solitary waves were manufactured using ERDIC's flume's ability to intake a wave maker position over time and generate that signal, which isn't offered in every flume. It was kind of cool that they were able to do that. As you can imagine, these high intensity waves resulted in beach bathymetry changes, which were these changes in beach bathymetry were accounted for by regrading the beach every 3 to 5 runs. And occasionally one run would cause so much change that we would have to adjust some of the profilers like the CCP pluses and ADPVs, even just between a single run. So yeah, so in the future, I'll be processing and analyzing some LiDAR data, starting with the Blickfeld Cube 2 LiDAR. I'm only a couple weeks into this process, but so far I've used Synology Drive for online data storage and sharing. And then I've taken the experimental data and used MATLAB to process and eventually interpolate the data to both display individual runs and then also show bathymetric changes between runs. So then the final topic I'm going to touch on today is how I got connected with the USACE Jacksonville district. This was, as I mentioned before, through the Smart Scholarship, which, if you aren't aware, it offers full tuition stipend, full-time civilian employment after graduation, and some more cool perks. But it's available to students ranging from seniors in high school all the way up to PhD candidates. The number of years a student is under scholarship corresponds to the number of years a student is committed to working for their sponsorship facility after graduation. In my case, that's the USACE Jacksonville district, but it can be any Department of Defense facility. So this application also involved citizenship verification and GPA requirement, along with uploading a resume, an essay, extracurriculars, reference contacts, transcript, and reference letters. So pretty intensive. This application is then sent out to the different DoD sponsorship facilities where they can then choose to interview and make an acceptance decision. Interestingly, you can, on the application platform, choose up to 5 preferred sponsorship facilities, but the sponsorship facilities can also choose to look at candidates who did not list them. So that was the scenario in my case. But just because you can choose these 5 preferred sponsorship facilities, you should still research the various DoD facilities and be knowledgeable on their background and your experience and where that could be best applied. I was lucky enough to be interviewed by the USACE Jacksonville district and was ultimately selected as one of their 2026 cohort of Smart Scholars. So from there, I just went on a site visit to the Jacksonville district over the summer and got to know my future coworkers. One of these coworkers was kind enough to elaborate on the tools I'm going to share with you all today, as you can see here. So as far as modeling, the Jacksonville District Water Resources Division performs analysis of tidal inlet hydraulics and sediment transport, numerical modeling of ocean and coastal waves and currents, surface water hydrology, hydraulics and hydrodynamics, 2D and 3D flow, and then integrated surface water and groundwater modeling, and then also water quality analysis and modeling, and even some more things. But getting into the specific models that they use, starting with Seashore, this is a cross-shore change model, and then CMS, the coastal modeling system, which is used for sediment and wave modeling. They were both developed by USACE. They also, at the Jacksonville district, use AdCirc or SWAN for modeling tides, surge, and waves for larger areas. And then they also use Delft 3D. This was mentioned earlier and is very popular in industry, but the Jacksonville district just started using it to model things like currents, waves, water levels, salinity, sediment transport, water quality, and more. So yeah, that wraps up my presentation for today. I thank you all so much for joining this call.
Thank you so much for your presentation again. It was great. So we are open to any question if you have, or also if you have any question and you watch the video, you can reach out to Wren by this email that we provided in the slide and ask her if you have any question about the project or how she got her positions. Thank you all.
Thank you.